Good morning. Uh, this is a rather short lecture compared to other lectures. The topic is obviously interpolation. What is the difference between interpolation and curve fitting? Let me give some introduction for that. So in curve fitting, we were given some data points. And we had to usually we were told fit a straight line or fit a polynomial, so we didn't have to decide that. For example, if the data points are something like this, we were asked to fit a polynomial through them, so we didn't really have to decide what that whether it is line or curve, but that was beyond the scope of the lecture. Again, it is not the topic here. But here in this lecture, what we are going to do is, if you are given some points, let's say x, if you are given some points, y, and then let's say another point, so that is the first point will be x1, y1, second one will be x2, y2, and then if you are given a third point, x3, where is going to be y3? Is it here? Is it here? That is interpolation. So here you were given too many points and asked to find the polynomial. That was curve fitting. Here you will just, based on, sometimes you will be given 3 points, based on just the right amount of points, how to find something to interpolate between, for any point in the middle. For example, for these 2 points, if you are given a point here, what is that interpolates between them? So very slightly similar. For example, you can do a curve fitting. You can fit a straight line through these. You can fit a straight line through these, and then find those. So you can say for any given point, x point, you can find a corresponding y. So that is definitely one approach. But in this lecture, we are going to study two approaches. One is Newton's different interpolation, other one is Lagrange interpolation. To interpolate the new points within a certain limit. So yeah, it is similar to curve fitting. Curve fitting can be used for interpolation for sure, but these approaches that we are going to introduce in the lecture are a little more, obviously more efficient and numerically stable than if we were to use the curve fitting approach for interpolation. The first approach for interpolation is the naive and direct method, which you will see later will be the first order Newton's method, naive method. So here you are given 2 points, 1 point here, 1 point here. For a given x, what is the y value? You just connect a straight line through those 2 lines, and then for this x value, this is the y value. You just find the corresponding value. So how to do that? You just fit a straight line using these 2 points. Using these 2 points, you fit a straight line, and for any given x, actually you can also do this approach for extrapolation. It will be less accurate, but it is possible. So that is the direct approach. You fit a straight line using those 2 given points, and then based on that you find the interpolation. So in summary, you need 2 points, x1, y1, we call it x0, y0, and x1, y1, and then for any given x between x0 and x1, you can find the y value. So that sums the naive approach. There's nothing that we didn't know before. Very straightforward approach. What we are going to focus is 2 approaches. Once again, is that these are very simple approaches, very intuitive and nice algorithms. So we will just review that now. First approach is Newton's divided difference interpolation. There's not really much theory, but there is a pattern That's what I want to point out here. So for first order interpolation, we write fx is b0 plus b1 x minus x0. So usually that's a linear equation. Usually we write the linear equation y is equal to mx plus c, y is equal to, in the polynomial in interpolation we wrote y is equal to a0 plus a1x, but here we are writing y is equal to b0 plus b1 x minus x0, where x0 is known. So we are going to definitely make use of the fact that x0 is known. So you'll see why. The goal here, is to find what is b0 and what is b1. That's all. That's what we need to know. So when you substitute in equation, when you substitute x is equal to x0, substitute x is equal to x0 in 7, you will directly get b0 is equal to fx0. Now when you substitute x is equal to x1 in 7, you can easily compute b1. That will come down to be fx1 minus fx0 divided by x1 minus x0. So we have a new notation for that. So we will call that f in square bracket x1 x0. Now let me rewrite the function. fx0 is fx0 is fx0 plus fx1 x0, that new notation that I introduced, fx1 x0 times x minus x0. That is exactly how we defined it. Now we found out what b0, and then b0 is fx0, and then b1 is f in square bracket x1 comma x0, which is defined here in 9. So that summarizes the first order divided difference interpolation. So you can give any value for x, and then you can find the interpolation. So that we just derived a formula for this. Let's go to Newton's second order difference coefficient. So here we, similar to 7, we write 12. So 7 and 12. So that's the first order equation. 12 is the second order equation. b0 plus, it is written in a special form. You need to notice that usually we write a second order equation as y is equal to a0 plus a1x plus a2x squared. But instead of writing that, we are writing b0 plus b1 x minus x0. We can totally write that because x0, x1 are known. So all we need to do is find those coefficients b0, b1 and b2, and obviously this is written this way because it is easy to find those coefficients. So like before, we can by substituting x is equal to x0 in 12, we will find b0. Substituting x is equal to x1 in 12, we will find b1. Substituting x is equal to x2 in 12, we will find b2. And then look at the pattern there. There is b0 is fx0, b0 is fx0, b1 is fx1x0, that is fx1 minus fx0 divided by x1 minus x0. b2 has this nice structure x2, x1, x0. We actually defined it, which is the difference between x2, x1. So that is the divided difference. You take the divide by the difference. So this is the difference, and then you have this special formula on top. So if x2 minus x2 x1 minus fx1 x0 divided by x2 minus x0. So that's the formula. So now we see a pattern. So now we can write this for the nth divided difference formula, the general scheme. So the general scheme divided different coefficients, so is written this way: fxn, fnx, where the n stands for the nth divided different coefficients. For example, each time we had those look, so this is the second order. So similarly, similar to equation 16, we are writing 17 as the general form. So obviously here we need to find b0, b1, all the way up to bn. But now we know the pattern. So b1 is, well, first of all, b0 is fx0, and then b1 is fx1 x0, b2 is fx2 x1 x0, so b3 is fx3 x2 x1 x0. Now we know how to compare them. So computing bt, we need b2, the formula for b2. So it is like it goes backward. So you need to have all the previous formulas to compute the other one. So that is what is shown here. You know, if you have x0 and x1, you can compute f x1 x0. Then using x2 and x1, you can compute f x2 and x1, which is fx2 minus fx1 divided by fx2 minus x1. This one is fx3 minus fx2 divided by x3 minus x2. This one is fx2 x1, actually it's square bracket, minus fx1 x0 divided by x2 minus x0. You know, we see the pattern there. And this one, fx3 x2 minus fx2 x0 divided by x3 minus x1. So this one, now we have three icons: f x3 x2 x1 minus f x2 x1 x0 divided by x3 minus x0. Now that's a pattern. So it tells us how to compute those. You can develop an algorithm for this. I did not provide an algorithm. I just left as an exercise. You can, I encourage you to write that algorithm so that when you write it, you will definitely learn more. Okay, so let's do an example for this. So here is an example, example 1. So estimate ln2 with the data points at 1, 0. ln1 is 0, so that's the first data point. ln1 is 0, and then ln4 is 1.386294 given. The goal is we need to find ln2 where x is equal to, that's what we want to find. So let's write the formula here. So f1x is b0 plus b1 x minus x0. That is a general Newton difference formula. We can only go the first order because we only have 2 points. If we had 3 points, next example we are going to do second order. So given 2 points, we can only do first order interpolation. So f1x is b0 plus b1 x minus x0, where f1x is ln x. We know that. I mean, I just wrote that because we know that, but we don't really. We are not going to use ln. We are not going to use a calculator to compute ln x. I'm saying that because of some of the homework I saw. So make sure you understand those, by reading the lecture again, listening to the lecture notes and stuff. Okay, so using the formula, we can easily find b0 is fx0, x0 is 1, and then b1 using the formula f41, and the difference, so f4 minus f1 minus 4 divided by 4 minus 1 comes to this. So we have b0 and b1. So we can just go and substitute here for b0 and b1. Now we can compute ln2 or ln3 for that matter. Anything between 1 and 4 we can compute. Since it is asked for ln2, the first approximation of ln2 is 0.46209 using the formula that we just derived. Example 3 is you are given 3 points. So 2 points are same as before. 1, 0, and then 4, 1.386294. These two are the same. Third point is given 5, 1.609. So that is ln 5 is 1.609438. We didn't need to know it is ln, but I'm just saying this is because that is the function is. Okay, so the third order Newton's formula is written here. Equation 28 is redundant. So we all, since the data points are the same, so that's the advantage of this Newton's divided difference formula. Since the previous points are the same, it is only true if the previous points are the same. B0 and B1 is already computed. It is not going to change. We saw that in the theory before. So only I need to compute B2, which we know that it is F541. That is F54 minus F41 divided by 5 minus 1. So if we just submit these, and F41 is already known, it is from here. So if you submit this, then we get a value for B2. Go back and submit there, we get a value for ln2 using 3 approximations. And here again, we were asked a fourth point is given, so we can go for the next interpolation, third order interpolation, and then the value is given. Just check out this very simple formula, and you can just try that. And the thing is, next is if you can program it, if you try, why don't you just try programming this, then that will give you a good complete understanding of this Newton formula. You can use the program that you wrote to do the homework. Even though you use your homework using your program, don't just paste your programming codes into your homework. You need to show the steps. Use your program to generate output, like how you would use a calculator to generate output. But then you need to show your steps in your homework to show that you understand the theory. Next, we have Lagrange interpolation polynomial. Here there's the theory. There's not really theory. The formula is given, but it tells how it works. The first order interpolation formula is x minus x1 divided by x0 minus x1 times fx0, x minus x0 minus divided by x1 minus x0 times fx1. That's the first order formula. For the second order formula, that is f2x, that is x minus x1 times x minus x2. You see a pattern. If this is a function is fx0, then x0 is not, and on the denominator x minus x1 and x minus x2 is there, and then it is x0 minus x1, x0 minus x2. Then the function is x1, no x1 at the denominator, but everything else is there. X minus x0 and x minus x2 is on the denominator, and then here x1 minus x0, x1 minus x2. Again, if the function is fx2, it is x2 minus x0 and x2 minus x1, whereas on the numerator, it is x minus x0 and x minus x1. So using this, I can write a general formula. The Fix is Fnx is I is equal to 1 to n fxi. If it is fxi, then this L is denominator is xi minus xj. J goes from 0 to n, all of them, and then x minus xj at the denominator, li minus xi minus xj at the x minus xj at the numerator, and xi minus xj at the denominator, sorry. And that is Lix, and as you can see, you have to compute Lix n times. So that is how you get the nth formula. So that would be a nice program to implement. Implementing this will be a good programming experience. Unfortunately, this is not in the lab this time. You have to do it on your own. But I would suggest, encourage you to implement this to Newton's method as well as this Lagrange to give you some good programming experience. That is one of the main goals of this course. Example, so same example as before. We need to compute ln2. I mean, when I say ln2, we don't really need to consider this ln2. You had to basically compute f2, where function, if you function fx, then it is x0, fx0, x1, fx1, and then x2, fx2 are given. So you don't really even need to consider this ln, but this is ln, so you need to understand that as well. So then just go and implement the formula here and you get the answer. You can check it again. For example, what is the second order approximation of newtons? So 0.581575, so you got the same result. So either the so if the points are the same, that's another point here. The forms of the Lagrange and Newton interpolation look different, but they are actually equivalent if the data points are the same. So important. So that's how we got the same answer, because they are indeed the same. That's why you got the same answer for the same interpolation. The Lagrange coefficients are easier to calculate since the divided down computation is not required. Yes, definitely Lagrange is easier to compute because it's just a formula. And the one drawback, if you will, of the Lagrange method is Newton method can be computed incrementally. If you got a new point all of a sudden, computing that new interpolation coefficient is easy. Whereas Lagrange, you have to implement everything again. So that's a small catch. Other than that, these two are the same methods. So that's it. So as I mentioned, this is a short lecture, and there are one or two. Try all the questions if you can. Probably first and second are assigned, or just the first, I'm not sure, assigned as your homework. So do that as well. Thank you.